You know, AI is everywhere, right? And a lot of the time, it kind of feels like magic. It's this mysterious box that just gives us answers, but never ever shows its work. So today, we're going to do just that. We're going to crack open that box and see what's really going on inside.
Okay, think about your phone for a second. You type in cat, and bam, there's every picture you've ever taken of your furry little friend. But how in the world does it know? I mean, you never sat down and taught it, this has whiskers, this has pointy ears, it just figured it out.
But here's the really wild part. How do you know it's a cat? Sure, you can list off the features, whiskers, pointy ears, a tail, but that spark of recognition, that aha, it's a cat moment, it's totally unconscious. You don't think about it, you just know. And believe it or not, that's the perfect way to start understanding AI's biggest mystery. And this right here, this is what we call the black box problem. We can see the data we put in, the input, and we can see the answer it spits out, the output. But everything that happens in between, the why, it's a complete mystery. It's all hidden away inside this so-called black box.
All right, so let's pop the hood and take a look inside. To really get what's going on, we have to start with the absolute basics, the building blocks of the silicon brain. Probably the easiest way to think about a neural network is to imagine a coffee machine. I mean, you put in the raw ingredients, right? The beans, the water, that's your input. Then something happens inside the machine. It grinds, it heats, it brews. That's the hidden part. And then out comes the result, your perfect cup of coffee. That's your output. A neural network, it's pretty much the same idea. So the most basic part of this whole thing is something called an artificial neuron. And right away, I want you to get the image of a tiny little brain cell out of your head. It's way, way simpler than that. Really, it's just a tiny piece of math. It takes a bunch of numbers, does a quick calculation, and spits out a new number to the next neuron in line. Seriously, that's all it does. Okay, so if these neurons are so simple, how does a whole network of them make a complex decision? Well, the secret ingredient is something called weights. The best way to picture them is like little volume dials all over the network. So when it's looking at our cat photo, the network learns to turn the volume way up on the pixels that show things like whiskers or pointy ears. And it turns the volume way down on, the boring wall in the background. Adjusting these dials, that's what learning is for an AI. And then there's one more piece to the puzzle, bias. You can kind of think of it as a little nudge for each neuron, like a tiny head start. It's sort of a default setting that helps a neuron make a decision even if the signals it's getting are a little weak. It just gives the whole system a bit more flexibility to find the right patterns. Okay, so we've got our parts list, neurons, weights, and biases. But how do these simple little pieces learn to do something so crazy complex, like spotting a cat in a photo? Well, it all comes down to one thing, making mistakes. A lot of them. This whole training thing is basically a 4-step cycle that just repeats over and over and over again. First up, the network just takes a wild guess. And since all its volume dials are set to random, its first guess is, hilariously wrong. Step 2, it compares its terrible guess to the right answer and calculates just how wrong it was. This is called the loss. Now, step 3, this is where the magic really happens. It's a process called backpropagation. The network literally works backwards through itself, playing a kind of blame game to figure out exactly which of those thousands of little dials contributed most to the mistake. And finally, step 4. It makes a tiny, tiny adjustment to those dials, and then it starts the whole cycle over again. Guess, check, blame, and correct. So, to get a little more specific, that learning process has 2 key players working as a team. You can think of it like a detective and a mechanic. Backpropagation, that's the detective. Its job is to investigate the crime, the wrong answer, and figure out exactly which weights are the main culprits. Then you've got gradient descent. That's the mechanic. It takes the detective's report, gets out its tools, and makes the fix by carefully tweaking those weights just a little bit to get closer to the right answer next time. Now imagine that cycle happening not once, but millions, sometimes billions of times. After all that trial and error, something truly incredible starts to happen. The network, which started out totally clueless, actually starts to discover the core features of a cat, all on its own, just from looking at the data. There was this famous experiment where Google researchers just fed a network a ton of random YouTube videos. They didn't label anything. And out of the chaos, one neuron basically taught itself to be a cat detector. No one told it what a cat was, it just found the pattern. It's mind-blowing. So this whole process is obviously super powerful.
But here's the catch. The fact that we have no idea how it's making these decisions, well, that leads to some really serious real-world consequences when the black box messes up. Because when the stakes are high, that black box suddenly becomes a huge liability. Think about it. A self-driving car gets into an accident, but we can't figure out why it made the choice it did. An AI denies you a loan, but the bank can't give you a reason because they don't even know the reason. This isn't just a tech issue, right? It's a huge question of fairness, of accountability. How can you trust a system that you can't even question? And this leads to one of the scariest possibilities, something called the clever Hans effect. This is the name for when an AI gets the answer right, but for a completely stupid reason. So imagine our cat spotting AI is 99% accurate. Amazing, right? But what if? What if the only reason it's so good is that every single cat picture we trained it on had a tiny little watermark in the corner? It hasn't learned what a cat looks like, it's learned what the watermark looks like. And we would have no idea because the why is hidden in the box. So this all sounds pretty bad, right? If we can't fully crack open the box, what are we supposed to do? Well, the good news is researchers are working on it. They're developing some really clever tools to help us peer inside. This whole field has a name. It's called explainable AI, or XAI for short. And the goal here isn't necessarily to make the AI think like us. It's more about building tools that can act like a translator, helping us understand why it made a certain decision. The whole point is to make these things more transparent, more fixable, and ultimately more trustworthy. One of the most popular and coolest XAI techniques is something called a saliency map. What it does is basically generate a heat map over an image, and it shows you the exact pixels the AI was focusing on most when it made its decision. So we can literally see, is it looking at the cat's ears and nose? Awesome, it's working. Or is it just staring at that little watermark in the corner? If so, we know we've got a major clever Hans problem we need to fix. But here's the thing. As we've built more and more of these tools to peek inside the box, we've stumbled upon a really profound realization. The reason the black box is so black isn't just because it's complicated. It's because the thought happening inside isn't just a faster or bigger version of human thought. It's a completely different kind of intelligence. Just look at the comparison. Our brains, they're biological wetware, super efficient, running on about as much power as a dim light bulb, but our signals are kind of slow. AI, it's silicon-based hardware, running at nearly the speed of light, but it can suck up enough electricity to power a small city. We learn from experience and relationships. It learns through pure mathematical optimization. And maybe the biggest difference, an AI's knowledge can be copied and shared with millions of other AIs in an instant. You can't just copy-paste a human brain. This bizarre mismatch is perfectly captured by something called Moravacs paradox. The paradox is this. It's relatively easy to make an AI that can beat the world's best chess grandmaster, something that takes a human adult years of training. But it is incredibly difficult, almost impossible, to give that same AI the basic physical skills of a one-year-old, like walking around a room without bumping into things. And why is that? Well, our intelligence was forged over millions of years of evolution to survive in the physical world. AI's intelligence was built from scratch to do math. So this is really the heart of it all. We are not dealing with a smarter or dumber version of us. We're dealing with two completely different kinds of thought. Our brains operate on a rich soup of context, emotion, and real-world experience. An AI network, it operates on high-dimensional statistics. When an AI sees a cat, it's not seeing a cute, fluffy animal that might purr. It's seeing a massive cloud of numbers, a statistical pattern of pixels that correlates very strongly with the word cat. It isn't finding meaning. It's finding math. And realizing that, well, it changes everything. The black box isn't a box of secrets we can't yet understand. It's a box that operates on a kind of alien logic that isn't based on human reasoning at all. It really is a different kind of intelligence. So the big question for our future probably isn't, can we trust it, or how can we make it think like us? Maybe the real question is, how do we learn to work with a partner whose mind is so fundamentally different from our own? What do you think?